Okay, let's start the talk now. Welcome to our seminar. Today we have Professor Max Welling. He's a research chair in machine learning at the University of Amsterdam and a VP of technologies at Qualcomm. He has a secondary appointment as a senior fellow. He has a secondary appointment as a senior fellow at the Canadian Institute for Advanced Research, CIFAR, and he's the co-founder of Cypher DV, a spin-off in deep learning which got acquired by Qualcomm in the summer of 2017. In the past, he has held postdoctoral positions at Caltech, UCL, and the University of Toronto. Professor Welling has a very interesting background. He actually started doing physics, doing his PhD in 1998 under the supervision of Nobel laureate Gerard Hooft. I think on this talk, we'll be able to see some of the influence this background in physics has on his work today. He serves on the board of NERDS since 2015 and has been the program chair and general chair of NERDS in 2013 and 2014. He was also the program chair of AI-STAT in 2009 and ECCV in 2016, and the general chair of MIDL in 2018. He has received many grants from Google, Facebook, Yahoo, NSF, NIH, NWO, and ONR, among which an NSF career grant in 2005. He is also the recipient of ECCV Kendrick Prize in 2010, and he directs the Amsterdam Machine Learning Lab, AM Lab, and co-directs the Qualcomm University of Amsterdam Deep Learning Lab, and the Bosch UVA Deep Learning Lab. He has more than 2,050 publications, among which there are many influential works, such as variation autoencoders, inverse autoregressive flows, or graph neural networks, on which he's going to talk today. Welcome to our seminar.
Thank you, Ferran, for the invitation and a nice introduction. Obviously, this is a bit new to me too. I'm looking at two screens. One is my own slides, and the other one is people watching me. I would, and I like that because otherwise, you know, talking to a screen is always a bit impersonal. So if you can, I'd love you to show basically your video. That's I kind of, at least I know people are watching me. So if you can't hear me, please start waving or something like that. That's fine. If things go wrong, just interrupt me. If things are terribly unclear, make sure you interrupt and ask questions as well. And I hope everybody is healthy there in Boston. Here in the Netherlands, we are in a somewhat similar situation, I'm sure. And I hope we can do these things in person soon again. Okay, so I'm going to talk about graph neural. Oh, I have some interference now. I'm going to talk about graph neural networks today. Basically, the big brains behind all these projects are obviously not me. These are the students and the postdocs and the colleagues who have been working much harder than me on these topics. And so there's basically two topics. One topic is on equivariant mesh CNNs, where Pim de Haan, Maurice Weiler, and Cohen are the co-authors. And then the other one is on neural augmentation on vector graph CNNs, where Victor Garcia is the main author and collaborator for that project. Okay, so let me first introduce to you geometric deep learning for a little bit. So in geometric deep learning, we try to do convolutions or deep learning on objects that are not necessarily 1, 2, or 3-dimensional grids. You could imagine studying the weather on the Earth, and clearly the Earth is a sphere and not a plane. Some people still think it's a plane, actually, but we all believe that's a sphere. And so then the obvious question is, how can you do convolutions on a sphere? The other one is, is social interaction data. And there the question becomes, how can you do convolutions on a graph? Right, so it's called geometric deep learning. It's machine learning that's not on non-Euclidean domains. And sometimes we have sort of convolutions which go under the name geometric or graph or group or gauge convolutions. And I'll talk a little bit about that today. And there's a wide range of applications in computer vision, graphics, social networks, chemistry, biology, physics, medicine, and so on. So if I want to sort of summarize machine learning in one slide, I guess this would be the slide, or even if it would be in one picture, it would be sort of this picture in the middle here. And it's basically, it's basically the idea that machine learning is a combination of inductive bias, which are your modeling assumptions, together with data combined to make predictions, right? So that is basically machine learning in one equation. But there's different kinds of scenario where you can do this. In the one end, you need a lot of inductive bias in your model because maybe there isn't a lot of data. Or maybe you want to train models that generalize very well out of domain. And in that case, generative models are sort of a very good solution to work with. And of course, Josh Tenenbaum at MIT has been a big proponent of that. And then on the other end, there is, machine learning where there is lots and lots and lots of data available. For instance, machine translation. And here is where the deep learning shines. And but the downside is that in this domain, you can, the upside is you can do very, very good prediction. The downside is that it's just very difficult to generalize out of domain. So if you train a model on white skin to detect sort of lesions, then as soon as you switch to a different kind of skin, it will horribly fail. And so the natural question becomes, so we all like sort of deep learning so much, how can we inject more and better inductive bias into deep learning? And sort of in this talk, I'll try to do this in two different ways. And so there's two parts to this talk. And the first one is to think about symmetries in the world. So symmetries play an incredibly fundamental role in physics. And so one natural question is, can we also include these symmetries in our neural networks? For instance, actually, the great sort of success of CNNs is basically because Jan LeCun figured out that translations are a really good bias, or translation invariants or equivariants are a really good bias to have in deep learning. Basically meaning that if you want to detect something in one side of the image, it would be similarly good to try to, you should use the same model as when you try to detect it on the other side of the image. But the question then is, can you generalize that to rotations or scalings or other types of transformations? So rotations are a nice group. Scalings on a grid is more like a semi-group. And maybe there is a larger class of transformations where we can do that too. And then, for instance, for graphs, the group turned out to be permutations. So if you present sort of a set of nodes as a vector, then you have chosen an arbitrary ordering of those nodes, and you know that that ordering cannot have any effect, so you need to then become equivariant under permutations of that choice of ordering of those nodes. So there's also a symmetry group, which is then the permutation group. So in this talk, we'll talk about sort of doing deep learning on manifolds, but then on discretized manifolds, on meshes, basically. Okay, then the second way in which we can include inductive bias is to actually use the generative causal direction of the world. And I am a proponent of the idea that the world is just a lot simpler in the generative direction, because that's the physical direction, that's the causal direction. And the laws of physics, certainly at the microscopic level, are incredibly simple and have very few parameters. Where in the opposite direction, as we'll argue, you need lots and lots of parameters, and that's why deep learning basically has a billion parameters in their networks. So we should use this generative causal direction. Often we do know a lot about that direction too, right? We know how the world works, so we can at least pose good models about the world in this causal direction. So we should use it, and then the question becomes, how do we incorporate that into our deep learning models? And I'll talk about that in the second part of this talk. And then we'll apply it to, for instance, MRI, reconstruction, MRI image reconstruction from a small subset of the observations that one typically have access to, or for instance, to channel decoding. So basically, or error correction decoding, where you get noisy bits on a noisy channel, and the question is how can you find the original bits back? Okay, so the first part is on equivariant mesh CNNs, and again, the co-authors here are Pim, Haan, Maurice, Weiler, and Cohen. Okay, so first a little bit on what is actually a convolutional neural network, and just view it slightly differently so that we can bring it as close as possible to a graph neural net. So if we look at this sort of figure here, so here's our little neural net, and there's these operations in this neural net here, which are convolutions. And a convolution, I'm sure everybody knows, but let me repeat it really quick. You have a little filter which you slide over the input image. You take the inner product of the filter coefficients with the pixels of the underlying image, and you then add the values up, and you store that result in the next layer. Now you can reinterpret actually that operation as a message passing operation. So typically there's not one filter map, but there's a whole stack of filter maps, as you can see down here. And you can think of if you take one pixel and you slice through sort of these activation maps, these feature maps, then basically you get a vector living on this one pixel here. So H1 is a vector living there. And now what we're doing, if we do a convolution around one pixel, is we take these vectors, we multiply the vectors with a matrix W, and the matrix W can now be different for every neighbor, because the neighbors, they're at fixed positions. Northwest is definitely something different from southeast. So these are different matrices. We multiply this vector by this matrix, and then we add everything up, and then we store the result here in the middle. So that's exactly the same operation, but now viewed as basically message passing on a graph. Now, what do we have to change when we go to a sort of an irregular graph, an arbitrary graph? Well, we have to realize that now that the grid isn't regular, which means that the number of neighbors might change. That's the first problem that we have. And the second problem is that the ordering is quite arbitrary, because I'm representing my graph like this now here, but I could just drag this particular node and I could sort of position it here. I would have some overlapping edges, but that's often unavoidable anyway. And now instead of having 1, 2, I have 2, 1 in this ordering, right? And so I have to basically, agree that there is no natural ordering in this graph. And so we have a symmetry. Our neighbors are basically a set. They are not a sort of an ordered set. They're sort of an unordered set. And so there is a permutation symmetry. And we have to sort of correct for it. And that the solution in this case is very simple. I mean, that's what the graph convolution basically is. It's you use the same matrix, W1. So instead of having all these different matrices, W1 to W8, you now have 2, one for the self interaction and one for the one that sends all the neighbors messages, and that's called W1. So now obviously, because they're all the same, you have solved both of these problems. And so that's basically what a graph CNN is. Of course, you then compose these things. Every node in the graph, they receive messages from their neighbors using the same matrix. You put nonlinearities in the middle, and you keep going until at the end you have an embedding of every node in a latent space. And if you look at it as an equation and write it basically as a convolution equation, you have one kernel which multiplies the feature at its own position here, this thing. And then there is another kernel, the neighboring kernel, which is shared between all the neighbors, which multiplies the features at the neighbors and sums them all up. Okay, now it looks like if you would have a signal on a mesh, and with a mesh I mean basically a discretization of a manifold, then you could just take your graph convolutional neural network and apply it to the nodes of that mesh and send messages over the edges of that mesh. And that is certainly a valid way of doing things. There's nothing wrong with it, except for the fact that it completely ignores the geometry. And the problem with that is that if you take a graph CNN, as I argued before, it is basically an isotropic kernel. You use the same kernel for every neighbor. And the point is that that's actually unnecessary restrictive. And so now what we're going to do is we're going to do the proper thing for a mesh on a graph. And my hope is that this we'll find lots of applications, let's say in graphics, if you want to do an analysis on graphics or generate things on manifolds, or in medical applications like this one where you have where people model arteries. Okay, so let me give one example of how a graph neural net is different from a mesh neural net. So here we have, we have part of a mesh, and we are going to send messages now from these neighbors here to the one in the middle. We first have to sort of move these points to the tangent plane. It's kind of a technical detail. So now we're in this plane here, and now it just looks like we are back in the Euclidean space, and we can sort of send messages from the neighbors to this point P. Now, a graph neural net would then, of course, take an isotropic kernel on this and would treat all the neighbors the same. And so it wouldn't make any difference between this and this one, because you know the ordering here is the same, but the ordering didn't matter anyway. And certainly here there is a bigger angle than there is here, but the graph neural net wouldn't even notice it, right? But that's clearly suboptimal because this is a different geometry than this one. And so now what we're going to do is we're going to properly define the graph operations, let's say, on this mesh. Now, the problem is that on a manifold, there is one issue which is kind of subtle but really important, which makes it very difficult to define these sort of kernels just straight out of the box. And the core of this problem has to do with this. So in the Euclidean space, it's quite easy to take a kernel like this, right, and then to move the kernel to parallelly propagate that kernel to some other point in your image or whatever flat space you have, right, and then share your kernel in this particular way. Now, if you look at this, let's first look at a Möbius strip, right? At a Möbius strip, you sort of start with your kernel, and then you know, it's a flat space, but it has a strange topology, and now you start to parallelly propagate that kernel all around, and then of course when you come on the other end, you find yourself mirrors relative to the one that you had before, right? And so there's nothing you can do about that, right? I mean, it's just basically the point is you cannot find any sort of handedness that is natural, because whenever you go around a circle, it will have swapped. I mean, locally things are well defined, but globally not. And similarly on a sphere, so if I take my little kernel and I move it like this, you know, I end up like here. But if I move it like this, you know, I end up rotated relative to this path. And okay, so here's the direct path, and here's the sort of other path. You see that this one and this one have rotated relative to each other. And so again, here there is some ambiguity that cannot be resolved globally, and that is an SO2 rotation in this plane. So I can rotate this frame, and there is no natural way of choosing that frame up to, you know, this rotation. And so I basically have to acknowledge that you know, this is something that cannot be globally defined. And what I'm going to do is I'm going to define a transformation law that says, well, you know, I can choose one frame on one part of my, you know, sphere and another frame on another part of my sphere. This is all fine, as long as I know how to transform from one part to the next one. So I can do all my convolutions, but I need to understand, if I move from one part of the sphere to the other part of the sphere, how do the results transform relative to each other? If I can do that, then at least locally, everything is well defined. Now, of course, globally, you know, you get this, you cannot get rid of this strange kind of holonomy effect, but locally, everything is perfectly well defined. And actually, it turns out that globally, you can also perfectly well define a convolution this particular way, but you have to mod out basically the symmetry, which is this orientation symmetry that you have. You have to factor it out. Okay, so then, so that goes to the sort of theory of equivariance, which Cohen has developed in his thesis. and many other people have followed up with lots of interesting work. And equivariance basically says if I have some function f which maps from x to y, so think of that as your convolution from x to y, and I also have some operation phi, so this is your symmetry operation, could be a rotation in my x-plane, and I have the same operation phi in my y-plane, then I'm going to say that this function f is equivariant if first doing the rotation and then the convolution is the same as first doing the convolution and then the rotation. So in pictures, that is like I have this little gecko here, an image of a gecko, and move the gecko someplace else or rotate it, right? And it doesn't matter if I first translate and then filter, or whether I first filter and then translate the gecko. So that's equivariance. In the mathematics, you have basically this commuting diagram. Now, that's mathematics, so let's try to look at this in terms of pictures. Here I have my image, this painting that we all know, of course. And then I can first do a rotation, and then I am going to do this convolution. This is a very special convolution. So let's look at the convolution. It is a convolution that has two feature maps, one for eyes and one for mouth, but it has 4 orientations. So the symmetry group is 4 90-degree rotations in this case, right? And I'm basically going to do the filtering under all 4 of these orientations. Now, what does it mean to be equivariant? But if I do my filtering here, I find, of course, 2 eyes in the mouth. So I find activations in these 2 feature maps. But if I rotate, then of course the image is rotated. So now I will find activations not in the first feature map, but I will find it in the second feature map. And also I will find them rotated. So as you see here, the activations are like this, but here they are rotated. Anyway, it is a well-defined transformation on the feature map, and therefore we can claim that it is an equivariant operation. Okay, so you can also view it maybe slightly differently. So if I have space here, I have some kind of feature vectors living on the space, which are the red arrows, right? And then in this direction, I basically have these 4 feature maps. So I have these 4 sort of circles here, which are rotated relative to each other. And then the equivariance basically says if I take a vector at point X and at level A, this has to be the same as in this next level, VA plus R, but then rotated around this axis, and also the vector V itself is rotated. As you see relative here, it's of course rotated here because it's pointing inward. Okay, so that's sort of the equivariance property. So now the question is, okay, what do we do with this equivariance? Right now we've written down the equations for equivariance. It's a constraint on the kernel. And I'll explain a little bit how this works in this mesh, in this complicated picture here. But in the end, what will happen is that we have a kernel, which is what we use to convolve the image with. And we're going to write down a constraint on that kernel. It's a linear constraint. We can easily solve it. We look at the non-null space of that equation, and that will give you a basis. And if you just use that subspace defined by that equation, then every linear combination of that basis will be equivariant. Okay, so let's look at a mesh. So here we have our little sort of meshed up, sort of curved manifold, and I'm going to try to do a convolution towards this point P here, a message passing from my neighbors to this point P here. Okay, so I will have to first pick a gauge, which is basically I will have to map this problem to a tangent space. So here's my tangent space. So I haven't plotted it, but it's like a sort of a plane which is sort of balancing on this point P here, and I've written it out here. But as I said, the orientation is impossible to naturally define. There's no natural orientation. You have to pick one. And I'm now going to pick the green point here, the green neighbor, as the 0 angle sort of gauge. Okay, and then once I have picked that neighbor, I can easily do my convolution and I get my answer. So this is on a graph, actually. This is a graph convolution, isotropic convolution. But I could have picked with, equally well, a completely different gauge, which is now I'm going to pick the red point here as my zero angle sort of gauge. So that's written out here. I can do a convolution in this space, and I get the same answer, some signal here in the middle point P, and these two will have to be the same now, or at least we need to understand what the transformation between these two is. Now it turns out this was an isotropic convolution, so they are actually invariant. It's exactly the same result. So that's valid, and that's a graph convolution. But now let's imagine that we don't have a scalar here, but we have a vector living on these points, as I said before. So here's our little vector. If I choose this gauge and I convolve, I basically I get this result. And if I choose this gauge and I convolve, I get this result. And now these results are different. But as I said, it's a meaningless difference. And the only thing I need to understand is how to transform this result into this result. And of course, that's just a rotation. And as long as I, as long as I use the kernels which satisfy this constraint, they are this result and this result are guaranteed to transform into each other under this simple rotation. Okay, that's equivariance. Now there's one, in order to properly define these things, there is basically two other things which complicate things a little bit. But in this work, we have tried to keep things as simple and close to a graph neural net as possible. And my hope is that will result in a wide adoption of this method, but you can make things more complicated. And so here's the equation for a graph neural net. This thing unfortunately is in front of me all the time, but so here is the equation for the graph neural net. Again, it's the self sort of kernel, and then it's the kernel of the neighbors, but the kernel of the neighbors is the same. And now here is the equation that we write down for the mesh. So again, the self part is sort of the same, although there is a constraint on this kernel. And then there is this kernel, which depends on theta. And that's actually new and different, because now this kernel is no longer isotropic. And of course, that's what we want. That's really important. It's more powerful than the one where we use the same weight for all the different neighbors. But there's also this term here, and I need to explain this term. And basically, this term is to, first of all, make sure that this P here and this Q are two different points on the manifold, and they may have chosen different frames. So I first need to match these two frames. And the second thing is I need to move this feature vector F, I need to parallelly transport it over the manifold from Q to P, because I need to get everything into basically the tangent plane of the target point P, right? And so in the Euclidean space, this is kind of simple, right? You move from here to here, and everything. The red line here is exactly the same, no problem. Of course, they could have different frames, and so I have to compensate for that different frame, which is just a rotation. That's absorbed in this row. But in a curved manifold, there is some other thing which is happening, which is actually I need to do parallel transport, which basically means if I start with this tangent plane, I first have to rotate it so it's aligned with this one. So it is now this one, and then I move it to this point. So that's parallel transport on a mesh, and it's kind of simple, and it's a discretization of what you would do on a continuous manifold. Okay, both of these operations are absorbed in this matrix rho, which compensates for these things. But then once you've done that, you're done, and now you have a very simple graph neural net, or mesh neural net, I should say. Okay, that's the end of the first part of this talk. I think I should just keep going and then wait for the questions until the end. Let me just quickly see where I am. I'm half hour, so that's good. So hold on your questions or write them down, and then we'll come back to it after I did the second part. So now the second part to recall is trying to come up with a different way to inject inductive bias into a graph neural net. And here the idea, this is what I call neural augmentation. And the idea is to use the generative forward model of the world, basically. And the claim is that generative models are easier to model than backward models, which you could think of as, or inverse models, which you could think of as a neural net. And just to give you an example, I hope you can sort of see this thing move, but when I look at this, I just get happy from the inside. It's just so beautiful. It's like these two galaxies which are being simulated, which then, collide. Of course, no star hits any other star because the distances are way too big. But we can We can simulate this at a time scale where no human would ever be able to observe this, but in our computer we can observe this, and only because we know the laws of gravity, right? And there's just super simple laws that will create this beautifully complex structure. Um, in actually, I would say that in all of machine learning, we're kind of obsessed with our deep learning architectures, but the rest of the science is basically has been using generative models and simulators and differential equations and all these kinds of things, basically to encode all of their inductive biases, right? So here are some simulators of earthquakes in California. This is a weather simulator. This is a simulator of a beating heart. But also in machine learning, actually, before deep learning hype was happening, or revolution, or how you want to call it, there was graphical models. And in graphical models, you can also think of them as generative models, like these. You imagine how the data get generated. Probabilistic programs is basically something that happened afterwards, which try to put these graphical models into a nice programming language. And then, of course, there's ordinary and partial differential equations, which most of the scientists use to express their knowledge. Now, in machine learning, we just went in the other direction, which is very fascinating if you think about it. So we take the raw input data, which is the pixels of the images or the audio sound, and we stick it into a very densely parameterized model like a neural net, and we try to predict properties of the world. Instead of going from the properties to the sensor readouts, we are going from the sensor readouts back to the properties of the world. And this is a difficult direction to model because it's not causal and it's not physical. But it is the direction in the end that we are interested in, of course, because this is what's making the predictions. And of course, these two things are related quite trivially by something you had in Statistics 101, which is Bayes' rule, right? You have a generative model, which is your model of data given class and properties and whatever, and there's some prior over classes and properties. And then you normalize, and then you get the discrete inverse model, which is the probability of the classes and the properties given the data, right? It's just Bayes' rule which relates these two models together. I'm going to quickly skip over this. So there's pros and cons to these black box and these white box modelings, but I think I've already said most of these things. Okay, so let's look at inverse models then. So inverse models is also a huge field, of course, in sort of the sciences. And what does it do? So you basically define your forward model, which you could think of as your decoder model. It says, okay, starting from something that I don't know, but I wish to know, latent variables, how does the data get generated? And this could be sensor readouts. In this case, it could be a blurring operation, for instance. Now, the inverse modeling says, okay, give me this blurry image and try to reconstruct the high resolution image, for instance, right? And you do that typically by so maybe a neural net or some convolutional neural net. Okay, so there's very many beautiful examples that sort of go through this paradigm, right? So I've worked a little bit on this problem, which is, so you have radio sources in the sky. Of course, you don't know precisely where they are or what they are, but you do measurements. You do measurements in the Fourier domain. And in fact, you don't measure all the Fourier components because it's a continuous signal anyway. So you subsample those, and you do that by having this array of antennas. They are located in some places, and it's basically their baselines which define the Fourier components that you can measure. You see this nice round patterns. That's because the Earth is rotating, and therefore also these antennas are rotating around. And now you could say, well, the easiest thing to do is to say, well, just take this signal, imagine that it's basically like this, do the inverse Fourier transform. And then, unfortunately, you get a very poor reconstruction of what you want. And what you really want is to go from here to here, or to go from here to here directly to do this. And the solution that you can do is you can put a lot of prior knowledge in the statistics of how these images look like. Or you can basically do some deep learning magic where you just train a model to look at many of these examples and try to reconstruct it for it. Of course, an image reconstruction and image super resolution, this is precisely what many people do. MRI is very similar. So basically you have an image you want to reconstruct, you you measure in the Fourier domain, you measure a small subset of them, and then you need to get back to that. If you do the naive thing, you get a very poor reconstruction. Here's another example, which is error correction decoding. So you start with a sort of a clean image that you want to transmit. Then you add some error correction bits to it. You send them through a noisy channel. On the noisy channel, you get this corrupted image, and then you send them through your inverse model. And the inverse model could be sort of belief propagation or some other error correction decoding algorithm that then cleans up this image. And this is a simulation which was, or this is a nice cartoon which was David McKay made. Okay, what are the traditional solutions to these problems? Well, typically you write down some objective function like a likelihood, and here is your generative model. It's the model of the sensor data given the unobserved data X that you like to reconstruct. You learn some prior, or you state some prior, which tells you what are the typical statistics of your image that you want to reconstruct, and then you just do you maximize this objective so you get the best possible reconstruction that's that satisfies the constraint of the observation model, but also is most likely under your prior. More sophisticated ones, for instance, the ones that are being used for error correction decoding, is belief propagation, where you send messages over the graph in order to find the most likely sort of marginal distribution, or the marginal distribution for a particular variable given the observed ones. But anyways, in all cases, this is an iterative optimization scheme, except for maybe the simplest possible examples where you can do it in one shot, but typically this is an iterative scheme. Okay, so that's what the traditional approach is. What do the deep learning people do? Well, they're lazy, right? They create a huge data set of X and Y data points. And then they say, okay, let me train a map that goes from X from Y back to X, right? So I stick in my noisy sort of image here in this architecture, which is called a UNet. There's all sorts of convolutions running in the middle and skip connections and all cool stuff. And then in the end, you get your reconstruction of your image or your segmentation or whatever you're interested in here. Okay, so that's the deep learning solution. But now the point I want to make is there's something in the middle, right? There's something in the middle where you use whatever sort of knowledge you have about the world, and you work one of these things around it. So you sort of combine these two things. So that's kind of at a high level the solution that I propose, which is the hybrid solution. So first of all, you unroll an iterative optimization scheme and interpret it as an RNN. So people have been working on that before. Sorry if I'm not putting any citations. That was a bit lazy of me. But so you basically take an iterative optimization scheme and you interpret that as an RNN. You then train a deep neural network around that to correct the mistakes that the iterative engineering solution is making, right? So you have a classical inference algorithm like a Kalman smoother or whatever else you have, but it makes mistakes. The world is much more complicated than a linear sort of model. And so what you're doing now is to train a nonlinear deep neural network around it to correct that model in the in the inference direction. Right, and then inside this neural network, there is this little data consistency term, which always figures out, always tries to test whether your current solution is still sort of consistent with the observation that you have been making, and you sort of incorporate that into your solution. So there is three terms. There's your engineering update, which is your classical update. Then there is the neural network, which computes corrections, and it's important that these are corrections because the correction signal is a lot smaller and more linear than the original signal, and also because this part is supposed to do domain adaptation well because it's based on physics, and this part, the correction, is hopefully then a lot more domain invariant. And then, of course, there's also these memory states, which we have sort of as a bonus because we're doing sort of RNNs and deep learning. We have these extra degrees of freedom which we can carry around to help our computation. Okay, so now we're going to do this on a graph because I promised to do this on a sort of to enhance a graph neural net. So and the easiest is to look at maybe error correcting decoding. So this is a low density parity check code where we have here are the bits. This is basically the signal that's coming in. It's a signal that says, you know, whether it's closer to a 1 or a 0, let's say. It's a continuous signal. And then there is these error correction bits, which basically is a checksum on some of these bits, and they're designed to check to 0. And now it's well known, and I won't go into the details, that we can solve this problem at least approximately, because it's a loopy graph, by sending messages from nodes to boxes, to factors, and from factors to nodes, iteratively until convergence, and then hopefully until convergence, and then read out, basically by taking the product of all these messages, read out what the probability at a node is, and that would be a good, you know, a good probability for the decoding. And for error correction decoding, this is a almost unbeatable solution. It's really, really good. Okay, so again, let me remind you of sort of a normal convolution as a graph message passing algorithm, and on a graph neural net, we use the same messages everywhere from all the neighbors. One way to write this is as follows. I want to go to the sort of notation, I want to move to the notation of message passing. So we have some hi and hj, which are these kind of these values here on the nodes. So I have some nonlinear function of the center node and the neighbor node. I might have some information a, which is living on the edge. I send all that through nonlinearity, and I have my message, which lives on the on the edge, and this message is sent from I to j. And then the second step is to collect, for every node, to collect these messages from the neighboring edges and produce the, you know, the estimate on the node M itself. And then there is an additional nonlinearity, which takes the old state at that node, the message that it has received, some other feature properties on that node, and pushes it again through nonlinearity to then update its state H. And you repeat that through different layers, and that's a GNN. It looks a lot like a message passing algorithm. Well, it is a message passing, but it looks a lot like belief propagation, I should say. Okay, so then the first thing we need to do when we're going to work on vector graphs is, of course, to generalize this to vector graphs. And so here, this is basically a copy of the previous slide. And actually, without trying to decode what this actually says, it's really simple. We're going to promote these vector graphs to, or demote, I don't know, to make them sort of normal nodes in a graph. And now we're going to just have two types of messages. We're going to have messages from these types of nodes to these types of nodes, and from these types of nodes to these. So we have two of these, but otherwise, the way that we update is exactly the same. We have it's identical. So we just say, you know, we have, you know, a special f for a node here, and a sort of subindex x for a node here. But anyway, these equations look exactly the same as they were here. So it's an almost trivial sort of extension of the normal neural net, graph neural net. Okay, and then I guess then, as this is sort of the engineering bit, now we need to build a circuit, and the circuit has to be such that we can backpropagate through it, right? So it's sort of the generalized notion of deep learning is sort of differential programming. So here we have basically a differential sort of operation. We put in our x, which is our noisy bits. We send it to the belief propagation, one iteration of belief propagation module. It computes messages. It sends these messages to the vector graph module, which takes them, does one step of vector graph message passing. It sends its results back here. These two things get added, so that this is going to be a correction to the belief propagation. This is going to be our new message that feeds into the new belief propagation module, and you repeat. Okay, until you do this for t iterations, you get some final answer out, you compare it to ground truth, you get a loss, and you backpropagate through the whole chain in order to compute, to change the parameters of these boxes. And of course, these are shared between all these boxes. Okay, this is basically, typically you just do this by pushing a button in PyTorch or whatever, right? And it will just do all this automatic gradient stuff for you. Okay, so now, of course, I left out details, and please read the papers to get to the details. Now let's just look at a few experiments to just see how this works. So this is a nonlinear Kalman filter. It's actually a chaotic system. It's called the Lorenz attractor. It's basically an ODE with 3 variables in 3 dimensions. So this is ground truth if you sort of generate sequences from this thing. Now we get some noisy data. So we run this, but then we noise up the sort of the points that come out. And if you just interpolate the noisy data, you get this. If you do a graph neural net, so you train a graph neural net, you get this result. If you do an extended Kalman smoother, you get this result. And if you do combine them, you get a very nice sort of result. And so that's sort of written out here. So if we, here's the number of samples that we use to train the model, right? And here's the accuracy or the error. So if you have very few samples, then clearly, you know, the Kalman filter is doing very well because it is a high inductive bias. The graph neural net does very poorly because it has no data to train on, but the Kalman filter is doing okay. And our method is basically doing as well as the Kalman filter. Now, if we increase the number of samples, the learning methods are bound to get better, right? And here you can see that the graph neural net is quickly surpassing the extended Kalman filter. So these are 3 types of Kalman filters. But the hybrid methods keep outperforming, you know, the graph neural net. We also tried this on LDPC decoding with a bursty channel. Oops. So here's a summary of the results. So in the bursty channel, you have a normal Gaussian channel, but so now and then 5% of the time you increase the variance on the channel, which is actually quite realistic if somebody walks through the sort of beam or something like that. And here you look at the variance of, you know, the burst that you give. And then here's the bit error rate. So LDPC codes are really, really good at low, you know, when this basically, when there is no burst, because then the model is perfect and you'll find it's impossible to beat. But then if you increase the burstiness, then even if you try the best you can and try to incorporate this burstiness in your model, the LDPC code will not do as well as the hybrid method. And actually even the GNN on factor graphs is catching up as well, but the hybrid method is still doing best. So we also apply this to fMRI imaging. It's not a graph in this case, it's more like an image. And so, but you can still apply the same idea. And Patrick Putsky here has worked on this problem, and he did very well with this framework. He first of all, he had to invent like the invertible recurrent inference machine, because otherwise these big 3D MRI images will not fit in memory. So he had to do this invertibly, in which you can sort of free your memory in the forward pass. And he basically won one of the tracks of this challenge, which was very impressive. I found that very impressive, at least. Okay, so then to conclude, as I said, machine learning is basically inductive bias plus data makes predictions. And of course, the name of the game really is how to inject the right amount and the right type of inductive bias, right? I mean, if you know precisely how the world works, you should basically use it. The problem is, of course, the world is always more complex than you can imagine. And so if you have a lot of data, then you should not waste, you should not put in too much of your biases, because you cannot overcome them with your data. But if you don't have a lot of data, your biases are probably bringing you better models. One way to inject inductive bias is to use the symmetries of the world. Translation symmetry brought us CNNs, and we've talked about permutation symmetry brings you graph neural nets, and then group engaged in mesh convolutions bring you all sorts of other nice, interesting convolutional neural networks. And actually, we are now working on natural convolutions, and that's an extension of graph convolutions, and so stay tuned for that work. And then the next part of the talk was about neural augmentation. So you combine classical message passing algorithms or classical inverse modeling solutions with neural networks. You wrap them around each other, and there's lots of interesting applications of this. We looked at error correction decoding, nonlinear Kalman filters, fast MRI reconstruction. And then there's this radio astronomy here on this side. So we were only tangentially sort of involved in this, but they were kind enough to make us co-authors. But basically, they did all the work, Morgan Stern et al. But it's a really, really cool application where you have a black hole in front of, say, a galaxy, and that creates a lensing effect. And so what you really see is kind of something like this. So this is the observed image, but this is actually, one of these galaxies, but it gets lensed very weirdly. And then the task is to reconstruct this image in the back here. And they used this kind of paradigm that I just talked about, and they got state-of-the-art results on it. I'm personally also quite excited about trying to use these ideas for contact tracing in the current corona crisis, but that's a whole different topic in itself. And I hope I didn't go over time too much, so I'll end there. Thank you very much.
Well, thanks for a great talk. Are there any questions?
Well, I have one. This is Bill Freeman. Hi, Max.
Hi, Bill.
Hey. So in these hybrid methods, there it seems is it obvious how to do the trade-off between the overly simple model, the generative model, and the more complicated deep learning one? Does that fall out, or is that a parameter you have to tweak?
Yeah, so that doesn't fall out in the methods that we use. So it's a very good question. So we had to use cross-validation to find the optimal trade-off. However, I think there is a Bayesian way in which you can sort of estimate that trade-off. And clearly, a Bayesian method should be able to figure out the relative strength of the two methods and automatically infer the trade-off. We haven't gone there, but sort of theoretically speaking, this should be possible.
Okay, thanks.
I have a question regarding the second part of the talk on the optimization. So you have multiple optimization steps. When you do many optimization steps, would you run into some type of instability?
Actually, no. So you have always a fixed number, and the algorithm is trained to deliver an answer after this fixed number, right? And so it's like the number of layers in a neural net, right? I mean, so you don't expect instabilities in the neural net at the top layer, right? So that's kind of the idea here too. So you backpropagate through T layers, and although the cost function tries to sort of do a bit of teacher forcing and sort of also try to penalize earlier reconstructions in this chain, in the end, it's the last reconstruction which counts and which it tries to get right.
And how large is T in this case?
It varies a lot, but typically 8, 10, 15, so that kind of order of magnitude.
Is it possible to learn the equivariant operations from data rather than building it in directly to the model?
Yeah, I get that question a lot, and it's a really interesting question, and we're trying to work on that. I think the fact that I'm working on it means that the question is yes, but we haven't managed to do it in a very nice way. So this is a really, I mean, it's complicated because I mean, groups are discrete objects in a way. When even continuous groups have discrete representations, which means that you have to sort of you have to even choose which representations to use, and so you even need representation theory before you can write down these equivariant functions, operations. But I think you can do everything approximately. So I think you could put, and we have one paper where we try this out, where you could put sort of a equivariance loss to a layer. You could say, I want if you do some kind of transformation in the input layer, I want that after you do your convolution, there is another transformation on the output layer which closes this commutative diagram. So I think you can put in these kinds of losses, and then automatically you might get some kind of interesting equivariances out. But I think the jury is still out on that problem, but it would be super exciting if somebody figures out how to find these symmetries automatically from the data.
Are there any more questions? Okay, cool. So since it's exactly 12, I'll end it here. Thanks a lot for a great talk. And thanks all for coming.
Yeah, thank you for inviting me. It was a pleasure.
Thanks, Max. Good to see you.
Yeah, same thing.